We're now going to examine how to create scatter plots with matplotlib. Suppose, as an example, you want to find how GDP per capita and life expectancy are related to each other in different countries. To do this, in our country's data, the columns you'll need to use are life expectancy and GDP per capita, as well as year, so you can find the relationship between life expectancy and GDP per capita for each given year. Let's now dive into a demo in which we're going to create scatter plots with the scatter function of matplotlib. We're also going to use the log10 function in the NumPy library as well. If you used Anaconda to install Jupyter and other libraries, you should already have NumPy installed because it comes with Anaconda. If not, make sure to install the NumPy library before you follow this demo. And we're going to use Python's for_item_in syntax to run a for loop over the given years. First, as usual, import pandas and pyplot. We're also going to import NumPy as np. Let's import our data with pd.readcsv as well. After that, let's first examine how GDP per capita and life expectancy are related in 2007, the most recent year that's available in our data. To do this, we're going to select the data for 2007 with data square brackets, data.year equals 2007, and we'll put it in a variable called data 2007. You can create a scatter plot with GDP per capita and life expectancy in 2007 with plt.scatter, data2007.gdp per capita, data2007.life expectancy. Show this with plt.show. You can adjust the size of each dot in this scatter plot with a third argument in plt.scatter. We can try different values to see which one looks right, but let's set it to 5 here. And let's add a title, an X label, and a Y label to make the graph easier to understand. As you can see, the higher the given country's GDP per capita is, the higher its life expectancy tends to be. We can double check this by finding a correlation between GDP per capita and life expectancy in 2007. We can do that with data2007.gdp per capita.core for correlation with the argument data2007.life expectancy. As you can see, GDP per capita and life expectancy in 2007 are highly correlated. Now, if you go back to this scatter plot, you might notice that GDP per capita and life expectancy don't seem to have a linear correlation. The life expectancy goes up very quickly when GDP per capita goes up in the lower range, but as a country has more GDP per capita, an additional increase seems to have less effect on its life expectancy. For example, this is evident if you compare the jump in life expectancy from a very low GDP per capita to $10,000 to the increase in life expectancy from $30,000 of GDP per capita to $40,000. So you might think that you should look at GDP per capita not in a linear scale, but in a log scale. To do this, we're going to use the np.log10 function. np.log10 is a NumPy function that computes the log of the given numbers with the base 10. So if we write np.log10 with the argument being a list of 10, 100, and 1000, it will give us 1, 2, and 3. This is because, of course, 10 to the first is 10, and 10 to the second is 100, and 10 to the third is 1000. Let's now make a scatter plot with GDP per capita on the log scale with plt.scatter, np.log10 of data2007.gdp per capita, data2007 life expectancy. This says draw a scatter plot not with raw GDP per capita, but with the log of GDP per capita with the base 10. Show this with plt.show. Now that the GDP per capita is shown in a log scale on the x-axis, if you look at 3 on the x-axis, it's 10 to the power 3 in raw GDP per capita, which is $1,000, and if you look at 4, it's 10 to the 4th, which is $10,000. This time, the graph seems to show more of a linear correlation. Let's find the correlation between the log of GDP per capita and life expectancy in 2007. It turns out it's about 0.8. Comparing it to the correlation between raw GDP per capita and life expectancy, you can see that the log of GDP per capita is more highly correlated with life expectancy in 2007. So this seems to be a more accurate model here. Now let's run this analysis for each available year in our data. To do this, we're going to run a for loop for each year. We're going to first find the set of all the years that are available with the set function. Then we'll make sure that it's in the correct order with the sorted function. Let's put this in a new variable called years sorted. After that, we can run a for loop for each year with for given year in year sorted. Select the data for this year with data year equals data square brackets data.year equals given year. Then make a scatter plot of GDP per capita and life expectancy with plt.scatter data year.gdp per capita and data year.life expectancy and 5. Let's set the title of this chart to given year and show the chart with plt.show. Once you examine these plots, you see that the ranges for the x-axis and y-axis are considerably different depending on the year. For example, in 1972, the x-axis shows up to more than $100,000, while in 1977, the x-axis shows up to only about $60,000. This makes them hard to compare with each other. And there's also an outlier with GDP per capita of more than $100,000 a year even in 1952. So let's set a consistent range for the x-axis and y-axis and ignore the outlier with plt.xlim 0 to 60,000, which sets the range for the x-axis to 0 to 60,000, and plt.ylim 25 to 85, which sets the range for the y-axis. Let's also add an x label and a y label as well. After all that, these graphs are much easier to compare with each other, so let's export them as images and examine how they have changed over time. We're going to do this with the plt.savefig function instead of running plt.show. The first argument in this function specifies the file name, and we're going to use str of given year here. We need to use the str function to convert the given year to a string because plt.savefig expects a string argument. And remember that DPI stands for dots per inch. This number specifies the resolution of the exported image. After exporting this image, we'll need to clear the current plot before drawing the next one with plt.clf. Once this for loop finishes running, let's see what the exported plots look like. In 1952, most countries' GDP per capita is less than $20,000. As years go by, GDP per capita keeps growing in many countries, and life expectancy keeps improving as well. Let's see this again. Personally, I think looking at these charts is very cool, so I would highly recommend reproducing this result by yourself if you haven't done so yet. Earlier, we ignored the outlier whose GDP per capita was over $60,000. But you might ask, which country was that one? Let's find it out with data square brackets data.gdp per capita greater than 60,000. It turns out it was Kuwait. They had close to $100,000 in GDP per capita from 1952 to 1972. Now let's draw a scatter plot for each year with life expectancy and the log of GDP per capita as well. We're going to make a scatter plot with plt.scatter. And the only difference in this line from the previous cell is the fact that we are using np.log10 of data year.gdp per capita instead of the raw values. Just like before, to deal with outliers and for more consistency, we're setting a consistent range for the x-axis and y-axis with plt.xlim and plt.ylim. And just like before, we're going to export these plots as images with plt.savefig. We're going to set the file name to be something like log 1952 for each year with log underscore plus str of given year. Let's examine what the exported plots look like. With these charts, we see the same pattern of continuous improvement that we saw earlier, this time with GDP per capita on a log scale instead of a linear scale. As we saw earlier, you can see that these charts show more of a linear correlation between the GDP per capita on a log scale and life expectancy. In fact, the log of GDP per capita has a higher correlation with life expectancy than the raw value of GDP per capita every year. I would recommend checking it yourself. In the next video, I'm going to give you an example problem to practice what you've learned in this video.